Okay, students, today I am going to explain the problems related to composition of functions as well types of the functions. That means one and onto nature of the functions. Let fx be a function whose domain is the closure interval minus 5 comma 7 and g of x equal to modulus of 2x plus 5. Then domain of f circle g of x is f circle g of x is. The given options are minus 4 comma 1 and closure interval minus 5 comma 1 minus 6 comma 1 closure interval, d is none. The composition of mappings f circle g of x, f of g of x, the domain of f of g of x is needed here. F circle g of x, f circle g of x is nothing but f of g of x. That means f of g of x is given modulus of f of modulus of 2x plus 5. But the domain of the function f is minus 5 comma 7. Since domain d of f equal to minus 5 comma 7, hence modulus of 2x plus 5 lies between minus 5 and 7 closure interval, hence I am taking equality also. Since this was defined over this domain, the variable modulus of 2x plus 5 must lies between minus 5 and 7. But modulus is positive, hence this is 0 is less than or equal to 2x plus 5 with modulus is less than or equal to 7. Hence minus 7 is less than or equal to 2x plus 5 is less than or equal to 7. Once removing the modulus form, we get 2x plus 5 lies between minus 7 and plus 7. That gives us minus 12 is less than or equal to 2x is less than or equal to 2. On dividing with 2, we get minus 6 is less than or equal to x is less than or equal to 1. So therefore, the domain of f circle g is minus 6 comma 1. Minus 6 comma 1. F circle g means initially you have to apply g and then f. Okay. That gives us f circle g of x. F circle g of x. F circle g of x, f and g, f and g. So f circle g of x. Okay. Hence the required answer is minus 6 comma 1. minus 6 comma 1. Next one. Next. If fx equal to 2x plus 1 by 3x minus 2, then f circle f of x, and second one is f circle of x. So this is if fx equal to ax plus b by cx minus a, then we know that f circle odd number of times, k times, equal to of x equal to, this is fx if k is odd and x if k is even. Once f circle f and so on, once you take k times operating on x equal to fx, in case of k is odd, once f is operating odd number of times, the fx is repeated. If f is repeated even number of times, then it takes x, because here x coefficient is equal to the constant involved in the denominator with opposite sign. So that is our concept. Based on this, therefore, the first one, f circle f of x, here odd number of times f is repeated, hence this is fx, that is 2x plus 1 by 3x minus 2. And whereas f circle f 4 times, even number of times f is operated, we get x itself. So this is one important point related to the composition of mappings. Next problem. Let gx equal to 1 plus x minus step x and fx equal to minus 1 for x less than 0, 0 for x equal to 0, 1 for x greater than 0. For all x, then f of g of x is equal f of g of x equal to g of x is 1 plus x minus step x, So that and fx is given as -1 for x less negative and 0 for x is 0 and fx equal to 1 for x being greater than 0. Then f of g of x is equal to. This is very simple problem. G of x is 1 plus x minus step x. X minus integer part gives us the fractional part of x. But fractional part of x lies between 0 and 1. Hence, that implies 1 is less than or equal to 1 plus fractional part is less than 2. So, that implies fx lies between, g of x. G of x lies between 1 and 2, more than 1. Therefore, gx is greater than or equal to 1, that is gx is positive for all x. Hence, f of g of x is clearly 1 since g of x is positive. By the definition of the function f, here once x is positive, fx is 1. Since it is positive, f of g of x is 1. Hence, the required value is 1. Here f of x equal to -1 for x like to signum of x, signum function. Here f is signum function. Signum function. Signum of size. Signum of x. Fx is signum of x is -1 for x negative, 0 for x equal to 0, 1 for x greater than 0. F is defined as signum function. Okay. And since gx is positive, then it is clearly 1. In case of x minus step x minus 1, this is fractional part of x minus 1. So, fractional part of x minus 1 is clearly lies between -1 and 0, -1 and 0. So that minus, of course, this is fractional part lies between 0 and 1. Taking fractional part -1, we get 0 and -1. It lies between -1 and 0. In such case, negative. So, in such case, f of g of x is -1. In case of g of x is defined as x minus step x minus 1. F of g of x takes the value -1. Coming to types of the functions. The function f from R to R defined as fx equal to x minus 1 into x minus 2 into x minus 3 is one but not onto. Onto but not 1. Both 1 and on, that means bisective and on. Neither 1 nor on. The nature of the functions, types of the functions. The given function is defined as x minus 1 into x minus 2 into x minus 3. If f is defined from R to R, then either f is 1 1 but not onto, or onto but not 1 1, or both 1 1 and onto, that means bijective, or neither 1 1 nor onto. So this is a polynomial clearly. The polynomial is given as x minus a into x minus b into x minus c, like that, in factors form. So draw the, clearly in such case, once you draw the graph of the curve, taking x equal to 0, we get negative, minus 6. So it passes through 0 comma minus 6. Taking x equal to 1, 0. At 1 comma 0, it is 0. It passes through 1 comma 0. Similarly, it passes through 2 comma 0. And it passes through 3 comma 0. So once you draw a smooth curve by joining these points, the graph is like this. The graph is like this. Okay, repeated values. It takes repeated values at 1, 2, 3. F of 1 is 0, f of 2 is 0, f of 3 is 0. Here, f of 1 equal to f of 2 equal to f of 3 equal to 0. That means once the function is defined from R to R, 1, 2, 3 is mapped to the same element 0. Hence, therefore, f is not 1, 1. It's not 1, 1. Whereas, observing the curve, there is, since it is a polynomial curve, there is no breaks in the curve. It is a smooth curve, no breaks and no discontinuity. So clearly it is onto. It is onto function. So here f is a polynomial, cubic polynomial. Of course, cubic polynomial. F is a polynomial of degree 3, whose range is R, the set of real numbers. That means whose range is, the graph is smooth enough and it takes all the values and moreover continuous, no breaks at all. And it varies from minus infinity to plus infinity. All the functional values lies between minus infinity to plus infinity. The range is minus infinity to plus infinity, which is codomain. Codomain R. So, since it is the polynomial range is minus infinity to plus infinity, because the domain is set of real numbers, x takes all the values of x. So correspondingly, fx takes all the values of x, all the real values. Fx takes all the real values. Hence, the range is capital R itself. That means codomain of the function f. Hence, since the range is equal to codomain, f is onto. F is onto. Therefore, f is onto, but not 1, 1. 1. So, here the function is onto but not 1, 1. Onto but not 1, 1. The second option is the right option here. Next one. Next problem. R and C denotes set of reals and complex numbers respectively. Set of complex numbers. Respectively. F defined from C to R. Set of complex numbers to R defined by f of z takes C value mod z is 1 1 on to bisective neither 1 1 nor onto okay. The function is defined from the set of complex numbers. The set of complex numbers to set of real numbers. So that z is mapped to mod z itself. Z is mapped to mod z. That means if z is a plus ib, where AB belongs to R, then mod z is the modulus of a complex number is square root of a square plus b square, which belongs to R. Which belongs to R. Okay, that is the modulus of a complex number. In such case, the given function f of z is equal to mod z is either 1 1 onto or bisective, neither 1 1 nor onto. Let z1 is 1 plus I, z2 is 1 minus I. Taking z1 as 1 plus I and z2 as 1 minus I. F of z1 is modulus of 1 plus I takes the value root 2. F of z2 is modulus of 1 minus I, that is also root 2. So, f of z1 equal to f of z2, which does not implies z1 equal to z2. These two are equal, but z1 is not equal to z2. Even though that f of z1 equal to f of z1, f of z2, z1 is not equal to z2. So, f of z1 equal to f of z2, z1 is not equal to z2, since z1 is not equal to z2. These two are different complex numbers. So, the concept of 1 1 nature of the function does not follows here. Both 1 plus I and 1 minus I are mapped to same element, root 2. Hence, the two elements of the domain map to one element of the codomain. Hence, f is not 1 1. Therefore, f is not 1 1. Again, f of z is mod z, modulus of z always greater than or equal to 0. This is always positive and so, otherwise 0. In case of 0 plus I 0, the modulus is 0. Hence, it is always either positive or 0. That means, therefore, f of z takes only positive reals. The range of, therefore, range of f is here or plus including 0 or plus union 0, which is not which is a subset of, clearly a subset of or codomain, which is a subset of codomain. Range of f is subset of codomain, or f is subset of codomain. It's not equal to codomain. Therefore, f is not onto. Hence, f is neither 1 1 nor onto in this case. F is neither 1 1 nor onto. Next one. Next problem. F defined from R to R is defined by Fx equal to Ax plus sin x for all x that belongs to R. Then A lies in the interval. Then if f is 1 1 function, then the interval in which A lies, then the interval in which A lies. This is one important one. Fx equal to Ax plus sin x for all x that belongs to R. And f is given as 1 1. F is given as 1 1. Then the interval in which A lies. Fx is given as Ax plus sin x for all x that belongs to R. Given f is 1 1. Given f is 1 1. That implies, of course implied, f dash x is either greater than or equal to 0 or f dash x is less than or equal to 0. Either greater than or equal to 0 or less than or equal to 0, either increasing or decreasing completely. Once the function is either increasing or decreasing, that must be 1 1. The function is 1 1. So therefore, f dash x greater than or equal to 0 implies A plus cos x greater than or equal to 0. A plus cos x greater than or equal to 0. But cos x lies between minus 1 and 1 implies A minus 1 is less than or equal to A plus cos x is less than or equal to A plus 1. But A plus cos x is greater than or equal to 0 means, therefore, A plus cos x greater than or equal to 0 from 1 and 2, of course, from 1 and 2. A minus 1 is positive, greater than or equal to 0. This is positive, hence it must be positive. So that implies a greater than 1. And a plus 1 is less than 0. Less than 0. A plus 1. Or in either case, or f dash x is less than or equal to 0 implies a plus cos x is less than or equal to 0. So that gives us a plus 1 is less than or equal to 0. So a less than or equal to minus 1. So either this one follows or this one follows, or therefore in both the cases f is 1 1. So f is 1 1. Then a greater than or equal to 1 or a less than or equal to minus 1. That is a belongs to or minus 1 comma 1, or minus of or minus of the open interval minus 1 comma 1. Excluding the values of minus 1 and 1, a takes the remaining real values. A takes the remaining real values. Of course, here f dash x is greater than 0. Here we will get closure interval. Strictly increasing, of course, not equal, of course. Don't take strictly increasing. So this is okay, a greater than. Similarly, this is strictly, once it is strictly increasing. Okay, that's right. Once it is 1 1, it is strictly increasing and strictly decreasing. A plus cos x, a minus 1 is greater than 0 here. So a greater than 1. In this case, a plus 1 is negative. This part is negative. Next problem. The function f from R to R defined by f(x) equal to 2 power x plus 2 power mod x is 1 1 and on to B. Many 1, that means not 1 1, and on to C. 1 1 and into function, that means not on to D. Many 1 on to. Many 1 on to function. f(x) is defined as 2 power x plus 2 power minus x. 2 power x minus 2 power minus x. For x negative, it is okay. For x negative, it takes this is the problem. Okay, let us take this. Fx is 2 power x plus 2 power mod x, which is 2 into 2 power x, for x being positive. Once x positive, mod x equal to x. For x negative, this is 2 power x plus 2 power minus x. For x 0, 2. So that is equal to 2 power x plus 1, 2 into 2 power x, in case of x being positive, and 2 power x plus 2 power minus x in case of x negative, and particularly it takes 2 in case of x equal to 0. In case of x equal to 0, in case of x equal to 0, it takes, function takes a fixed value. Function takes a fixed value. In such case, the nature of the function. In such case, the nature of the function is. To check whether it is 1, 1 and on 2, let us check the monotonicity of the function. Once it is monotonic, that means either increasing, monotonically increasing or decreasing, it is clearly 1, 1. Strictly monotonic and strictly either strictly monotonic increasing or monotonic decreasing. Then the function is clearly 1, 1. So for that, let us observe the first derivative, f dash x. Taking the derivative of this one, for x being positive, derivative is, of course, 2 power x plus 1 derivative. Exponential derivative is itself 2 power x plus 1 into log 2 to the base, and derivative of x plus 1 is 1 for x positive. For x positive. In case of this is 2 power x minus 2 power minus x into, of course, log 2 to the base e for x negative, and this is 0 for x equal to 0, x equal to 2, x equal to 0. This is the derivative of the function. For x positive, clearly this is positive. This means f dash x is positive in case of x greater than 0. Okay. In case of x negative, x being negative, it becomes x negative minus x is positive. So 2 power x minus 2 power x in such case is 0. So that f dash x is either positive or 0. Hence it is clearly, or otherwise 2 power x is more than 2 power minus x for all x. 2 power x is more than 2 power minus x for all x. So in such case, x negative, once x is negative, then what happened? Let us take this value. Let us take x equal to minus 2, x negative, then 2 power minus 2 minus 2 power 2 square. That is, it takes negative value in case of x being positive. X being greater than or equal to 0, f dash x is increasing. Okay. This is x negative. It cannot be positive, of course. It cannot be positive. This is clearly negative because x takes the value minus 2. It is f dash of minus 2 is 2 power minus 2, 2 square. Of course, log 2 positive. This is 1 by 4 minus 4, negative, clearly negative. So, for positive reals only, of course, let us observe that whether the domain is or plus here. The given domain is only or. Okay. F dash x is positive for all x being greater than 0, monotonic increasing. And f dash x is negative for all x less than 0. Of course, it is equal to 0. X being equal to 0, this is 1, f dash x never be 0. Okay. At x equal to 0, that is 0. F dash x equal to 0 for all x equal to 0. In such case, for x being positive, function is s. Okay. As x increasing, clearly here as x increasing, this is increasing. So, totally monotonic increasing. Okay. The value is increasing. Even though it takes negative value, it is increasing. As steep increasing. So, here f dash x is positive for x greater than 0 and f dash x is negative for x negative. So that therefore 0 means f of 0, this is f of 0, therefore f is increasing function. F is increasing. As x takes the negative value, f dash x is negative means, though it is negative, the values of the function derivatives are increasing. So, f is increasing function. So, f is 1 function. It is 1 function. Okay. And range. Coming to range, to get onto function nature. Here range of the function. Here fx is greater than 0 because exponential. Since exponential is positive. Is positive. Therefore, range of f is or plus only, which is a subset of codomain or. Codomain or. Therefore, f is not onto. The codomain is not equal to range. Hence, f is not onto. Hence, it is 1 but not onto, that means into. So, 1 and into. C is the right option. Here C is the right option. The concept is clear. Here f dash x is greater than 0. X less than 0, then f dash x is less than 0. That means x is increasing from negative end to positive end. These values are also increasing here. So, hence totally increasing. That is the concept here.